We are on our last lesson today. We're on our last lesson today of Euclidean geometry. We're moving on to analytical geometry on Monday, and analytical geometry is really nice. You've actually done most of it by the time you get to matric. There's very little new work that we do in matric, but we are going to do our analytical geometry course. So that's happening on Monday. Then we have looked at, within this Euclidean geometry course, similarity and proportion. That's a new stuff in matric. Now, I've said this to you before, it is not a huge part of the geometry in paper 2. The majority of the geometry is circle geometry. And you're going to see as we go through some of the questions, even this question, this example 4 that we did on Monday, a lot of the questions will be circle geometry based. And then at like a 11.3, 11.4, we'll bring in similarity and proportion. So they do go hand in hand, they go in together, same as similarity and proportion are often asked together. So that's why it's so important, and that's why I say up here, you have to be revising your Euclidean geometry, because most of your Euclidean geometry is circles, and then a question or two on similarity and proportion. All right, but let's get into it. So today we're looking at exactly how it's going to be examined, so exam questions. This first question is quite old, 2014, so that's 10 years old. The reason I put it in though is because of the quad. Often we forget our properties of quads and then we're left stumped, and this will come up a bit more as well when we talk about analytical geometry, because analytical geometry is another section where we test quads. But you need to know your properties of your quadrilaterals. If you don't, like I say, you're going to be left stumped. So we need to know the properties of our quads, and this is why I've chosen this 2014 question, because of the fact that it deals with a parallelogram, and we're going to use properties of a parallelogram to answer the questions that we have here. All right, so this is in the diagram, ABCD is a parallelogram. The diagonals of ABCD intersect at M. F is a point on AD such that AF to AD is equal to 4:3. E is a point on AM such that AF is parallel to BD. FC and MD intersect at G. So there's a fair amount of information going on here. So let's break down what we have. So the first bit of information we were told is the fact that we're working with a parallelogram. So ABCD is a parallelogram. I'm going to highlight that in purple. I know it seems a bit silly, but knowing what's what is really important to answering your questions. So ABCD is a parallelogram. The diagonals intersect at M. That's fine. We can see point M. We've got no problem there. The next important bit of information is this ratio. AF to FD is 4:3. Here's AF. Here's FD. This is 4 parts. Because remember, it's a ratio, it's not a length, to 3 parts, which does actually mean you know the whole length AD is 7 parts. Okay, this will all become important a little bit later on as we go through. We were then told that E is a point on AM such that EF is parallel to BD. So EF is parallel to BD, so one of the diagonals of your parallelogram. That's also going to be important because obviously we know that opposite sides of a parallelogram are parallel, but now we've got 2, let's call them random parallel lines here. Great. So the first question is asking us for a ratio. Let's just make this a smidgen bigger. And it's asking us for the ratio of EM to AM. Great. Let's go find those sides, because all well and good, but if I have no idea where they are, it doesn't help me. So EM, AM. Here's EM. AM is that whole side length. They are 2 completely random line segments. I say completely random. They're not like sides of my parallelogram. AM is half of the diagonal. EM is a line segment on that diagonal. So we now just need to think carefully. This is now where you go back to the information you were given and you have a look and you see what information were you given that's going to help you. And the information you were given here that is going to help you was this AF to FD ratio, because hopefully what you can see in this yellow triangle is that AF is in proportion to AE and FD is in proportion to EM, which means that we can set up, using proportionality theorem, the ratio for EM to AM. Okay, so we know that EM over AM, okay, we're gonna just keep trying, EM over AM is equal to, now you match it up, EM matches up with FD, the whole side length AM matches up with the whole side length AD. Prop theorem, or you can use line parallel to one side of triangle, it doesn't really matter. State your parallel lines if you're using prop theorem, EF parallel to MD, or you can say BD, it really doesn't matter. Now that we have that, we can go fill in what we know. So we know that FD, because we were given it, is 3 parts, and AD, so the whole side length, is 7 parts. That's my ratio of EM to AM. Simple as that. Nothing more complex. I don't need to overthink it. I have all of the information right in front of me. Okay, so you're going to try the next one. And the next one is asking us for the ratio of, silly thing, CM to ME. So again, we're just going to identify where that is. CM is this diagonal down here, to ME is this portion over here. Now remember, we've just worked with ME, so you do have that bit of information. Use what you've got. Right, so I'll give you 2 minutes. Sorry. I want you to work out what that ratio is for me. And I'll give you a hint. Use your properties of a quadrilateral. And specifically, this is a parallelogram. Remember, you can put in the chat what ratio you get once you have one, so we can see. Hey, let's have a look. All right, so remember, you have some information that is going to be useful here. You have already proven that AM is 7 parts, okay? And that EM is 3 parts. That's bits of information you already have. Now remember, diagonals in a parallelogram bisect each other. So if AM is 7 parts, CM is also 7 parts. So when we set up this ratio, we can now use that bit of information. We first obviously need to say that we know that AM is equal to CM because of diagonals of a parallelogram, and you can abbreviate that to PALM. You don't have to write a parallelogram, bisecting each other. And so therefore our ratio of CM to ME is 7/3. So use information that you have. Don't try and reinvent the wheel. When we ask you questions like this, where there's a 9.2, 0.1, 0.2, 0.3, oftentimes the information you found in the previous question or questions is going to be helpful in questions later. So always go back to what you already know and see if it's going to help you. So 9.2.3 is asking areas. I'm just going to split up so we've got some space. The area of triangle FDC to the area of triangle BDC. We're going to have a lot of colors going on, but we're just going to work with it. So FDC is this long skinny triangle down the side of my diagram over here. And BDC is the much larger triangle. Let's go in the darker green over there. So those are the areas or the two triangles whose areas I'm comparing. All right, so I want you to take a second, and the first question is, how do you work out the area of a triangle? That's my first question to you. You can unmute yourself, you can just type it in the chat. How do you work out the area of a triangle?
Ma'am,
Yes.
isn't it half times base times height or length?
Perfect. Half base times the perpendicular height of your triangle. Awesome. Does anyone know a second way that we can work out the area of a triangle? I know I'm putting you on the spot. There's 2 ways we can work out the area of a triangle.
Ma'am,
Yeah, Siva?
by using the sine rule.
Okay, almost our area rule. So the area rule tells us that we will take half AB times sine of angle C. Perfect. And guys, just remember so that we know what's what. The angle C is then in between the sides A and B. So that's what we're talking about when we say half AB times sine C. So it's 2 sides and the included angle. Awesome. So those are 2 ways that we can work out the area of a triangle. Important to just remember. Okay, so now that we know how to work out the area of a triangle, if you think about half base times height, and we only really ever use the trig one when the angle is common. And in this case, because of the triangles and the way they're positioned, there is no common angle here. So I'm not going to use the area. If we think of half base times height, I want you to look at the 2 triangles that I've beautifully highlighted there. And I want you to tell me what is the same in both of those triangles. So think about half base times height. What is the same in both triangles? Okay, so just careful, angle D, the full angle D is in triangle FDC, but only part of angle D is in triangle BDC. So just be careful, we don't have the full angle there. Okay, there's actually two things that are the same. Either you see that the base DC could be considered the base of both triangles of the blue and the green, but more importantly than that, whenever you have got two triangles that exist in between parallel lines, so from one parallel line to another like we have here, what that means is that your perpendicular height is the same. So if you think about the perpendicular height for the blue triangle, that is exactly the same as the perpendicular height for the green triangle. And so when you think about the area rule, you've got half base times height divided by half. Let's try that again. Oh, why does it hate me? Okay, half base times height divided by half base times height. What that means is because your heights are the same, they divide away. And a half divided by a half is 1. So by finding the fact, or by seeing the fact that those heights are actually common or the same height, when you go and substitute, and you don't even need to substitute in a height there because you know they are going to divide each other away, leaving you with just 1. And so what we actually have here is a ratio of the bases. Now, if this is my perpendicular height, I'm fully aware there's a lot going on in my diagram. If this dotted line is my perpendicular height, the base length of the blue triangle is FD. If this dotted line is my perpendicular height, the base length in the green triangle is BC. So we've got FD over BC. Now let's go back and see if we know that information. For FD, we know it's 3 parts. BC, we don't know, but we know that this is a parallelogram. What do we know about opposite sides in a parallelogram?
By 6.
Okay, sorry, let me rephrase my statement. What do we know about the opposite external sides of a parallelogram? So what do we know about AD and BC? What is their relationship with each other? No, you know this. Opposite sides of a parallelogram are? Nice, Bongi and Kosi, they are equal. So if AD is equal to BC, and we know that AD is 7 parts, BC is also 7 parts. So our ratio here is 3:7. And what you'll start to find is that when you do have triangles where the heights are the same, when you're looking for the area, actually all you're looking at is the ratio of the base lengths. Okay, so as you can see, and this is why I chose this question, knowing the properties of your quadrilaterals is really, really important because it allows you to find bits of information that potentially we don't know. So we didn't know BC until we figured out the properties of our quad. What I will do is I've got a summary somewhere for the properties of quads. I'll put it on the Google Classroom just in case you need it, and it is just going to be useful for analytical, but just as a reminder. All right, guys, but let's take a screenshot of this and then we'll have a look at the next question where we're now going to bring, oh golly, now where we're going to have a look at some circle theorems that are going to help us with similarity and proportion. And remember, as we go, if you have questions, please just ask. Okay. So if we have a look at our second example, we have this beast. It says example 2. I'm not going to stress about it. This was taken from 2021's November paper, 2021. And this is more sort of what you can expect. I'm not saying you can't expect a question like what you saw in example 1, where it was a quadrilateral. You definitely can. but 99% of the time, proportional similarity is integrated into circle questions. So this is what you can look forward to come June, mocks, and December. Not December, November. Right, so let's read what we have. PK is a tangent to the circle at K. Chord LS is produced to P. N and M are points on K, P, and SP respectively, such that MN is parallel to SK. Chords KS and LN bisect at T. So there's a lot of information there. Let's just be mindful of what we have. So we were told that PK is a tangent. Now, the second you are told something is a tangent, you should automatically be thinking tan chord and tan per brad. In this case, we don't know where the center of the circle is, so tan per brad is not relevant for us. Tan chord, we should be thinking about. Okay, when we are told that a chord is produced, so here it says chord LS is produced to P. Here's the chord LS. Produced just means it's extended to meet at point P. That's all it means. There's nothing special about produced. So we've got a chord, it's extended, great. And then we're told that because of where the points, sorry, let's just get rid of this. Where the points N and P are on the chords KP and SP, or the lines KP and SP, MN, so in blue here, is parallel to KS. Now, grade 12, what I want you to remember is that we never give you useless information. The fact that I've given you a tangent, somewhere you're going to have to use tan chord. The fact that I've given you parallel lines, somewhere you're going to have to use those parallel lines. Corresponding angles, alternate angles, co-interior angles, they're given to you for a reason. Okay, and then we're told that chords K, S, and LN intersect at T. We can see coordinate T there. So the first question is asking us to prove that K4 is equal to NML. So K4 up here in the red dot, NML is this angle over here. So basically M2 and M3 together. So I want you to tell me, or I want you to go and prove that those two angles are equal. I'll give you 2 minutes and then we'll have a look, but prove that the angles I've shown there in red are in fact equal to each other. Okay. So the thing that we need to be mindful of here is the fact that I can't immediately just say that they're equal. There is no geometric reason that tells me straight away that K4 is equal to NML. So now I have to start looking at, okay, well, what angles are equal to K4 and what angles are equal to NML? Now you can start wherever you want, it doesn't matter. But if I look at K4, because K4 is the angle created between the tangent and the chord, I know, and let's try and do this as well as we can. I know that because of tan chord theorem, angle S1 is also going to be equal to K4. Tan chord theorem says that those two are equal. Cool, that's fine. If I look at NML, NML is an angle created from that parallel line MN, which means that corresponding angles means that NML is equal to S1. Now, if both of those angles K4 and NML are equal to S1, then they both have to be equal to each other. And so that is the logic we're going to use now to go and write all of that information down to show that those angles are equal. Okay, I'll put the red back in a second once we've proved it. So the first thing I said was that angle K4 is equal to angle S1 because of tan chord theorem. I also said that angle NML was equal to angle S1 because of corresponding angles. Remember, whenever you use parallel line reasons, you have to state the parallel line. So in this case, it's MN parallel to KS. And so therefore, K4 is equal to angle NML because they are both equal to angle S1. Now, you're more than welcome to make that statement that they're both equal to S1. That is the reason why that why they are equal. And so now we know K4, S1, and that whole angle there, NML, those are all equal to each other. So all the red dots, those angles are equal to each other. Let's actually do curvy lines because it's multiple angles. Now, the reason I'm putting that in on my diagram is that might be useful for me later on. Remember, everything we do has a reason. Question 11.2b asks us to prove that KLMN is a cyclic quad. So let's look at where angle KLMN is. KL to M to N, all the way back. I want to prove that that thing highlighted in green is a cyclic quad. Now, there are three ways to prove that something is a cyclic quad. Obviously, you don't do all three, you just pick one. Excessively thick. Let's change that. First way is to prove your exterior angle is equal to your opposite interior angle. Second way is to prove that opposite interior angles equal 180 degrees. And the third way is to prove that angles in the same seg are equal. Those are the three ways that you can do it. So remember, we have just proven a bunch of angles equal, and all three of these ways involve angles. So take a look at the angles we've proven are equal and see if any of them allow you to say that KLMN is a cyclic quad. Any ideas? Nice, Bongi and Corsi. Okay, so Bongi and Corsi has said, well, K4 is equal to MNL. NML words. So this angle here is equal to this angle down here. K4 is an exterior angle to the cyclic quad that we're trying to prove, or to the quad we're trying to prove is cyclic. And so therefore, because K4 is equal to angle NML, L. Now, this was not given to you, but you have just proven it. You don't need to reprove it. So your reason is just proven. Therefore, KLMN is a cyclic quad. And you can phrase your reason slightly differently. It just depends what you've learned. I use converse exterior angle of cyclic quad. So whenever I'm proving a cyclic quad, my reasons will involve converse, or you can say exterior angle of cyclic quad equals opposite interior angle. That's absolutely fine as well. As long as you're getting across the fact that you know because the exterior angle is equal to the opposite interior angle, you have a cyclic quad, you're fine. Right, so now we know that KLNM is a cyclic quad, and because you've proven it, any further questions that you now answer, you can use cyclic quad theorems in KLNM. KLNM. All right, so leading that or taking that information, oh, guys, I can't speak English tonight. Taking that information and leading us into 11.2.2, we want to prove that triangle LKN is similar to triangle KSM. So all I've done is I've just put the diagram here again for us. I'm going to fill in or just indicate what we know. So remember, we know K4, don't know why I'm doing that, S1 and NML are equal to each other. We know that PK is a tangent. We obviously have our parallel lines. NM and SK, KS, whatever you want to call it. And we've just proven that LKMN is a cyclic quad. So these are all things that we know that are potentially going to help us prove similar triangles. Now, the triangles in question that what we are wanting to prove are similar are as follows. LKN, let's do this. So LKN in pink, this pink triangle up here is similar to, and we'll do this triangle in panic, dark blue. I give up. KSM. So this triangle over here. You want to prove those triangles are similar. So you're going to try by yourselves. That's all the information that you know. Use what you know. And remember, the fact that I've given you no information about your side lengths means that you're probably going to have to prove angle, angle, angle for similarity here. And because you have to prove angle, 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 think about the angles that you know are equal. Think about the angles you know are equal because you have proven KLMN is a cyclic quad. And remember, once you have two angles, you automatically know the third one is equal to the other. Right, so I'll give you 3-4 minutes, and then we'll have a look at this similarity proof here. Right, so there's a question of, can we say angle K is common to both triangles? Just be careful. We can't say that because different portions of K are in both triangles. So in the pink triangle, you've got the whole angle over there, K. Whereas in the blue triangle, you only have K2 equal. So because they're not the same portion or the same value of K, we can't say that it's a common angle. They have to overlap perfectly in order for it to be common. Give you 1 more minute, then we'll have a look. And remember, guys, you've proven a whole bunch of stuff. You've just proven it's a cyclic quad. You've proven the tan chord angle and the corresponding angles. Use that information that you already have to help you answer this question. I know it isn't that easy. I do understand that, especially because this diagram is quite complex. But start just by saying, okay, well, if it's a cyclic quad, what angles are equal? All right, just to help us a bit better, I'm going to just take off this green highlighter. Apparently I'm taking off the pink as well, but I'll put that back on now. Yes, remember we're looking in the pink and the dark blue triangles. So like I say, start with, you've just proven it's a cyclic quad. What do you know? Now remember, cyclic quad reasons are opposite angles of a cyclic quad add up to 180. Exterior angle of the cyclic quad equals opposite interior angle, and angles in same seg. Now, if you go and have a look, we have got lovely bow tie shapes. Not help if I could draw a bow tie here. Let's try that again. We have got, can't draw a bow tie to save my life. I'm now going to panic at this whole situation. Okay. Let me go another direction. No, it didn't help. We've got bow ties. I don't know why I can't draw a bow tie right now. It's clearly making me panic, which is ridiculous. But anyways, I'm panicking about the bow tie. But anyways, yeah, Emmanuel, I don't know. I could draw it perfectly fine earlier. Don't know why I can't draw a bow tie right now. I'm gonna try one more time. Okay, let's see if I can do it. Haha, I can do a bow tie. There we go. Okay, I feel better about myself. Bow tie. M3 is equal to N3. N3 is an angle in the pink triangle. M3 is an angle in the blue triangle. Awesome. Angles in same seg. I've proven that those two are equal. Right, let's take that hideous bow tie off. So we know that N3, okay, apparently not. Let's just grab this. N3 is equal to M3 because of angles in same seg. All right. We've got that. I have to draw another bow tie and now I'm just terrified. Okay, I'm gonna try my best. If you now have a look at this green bow, it shouldn't be this hard. If you have a look at the green bow tie that I'm gonna get right on my second try. I'm psyching myself up. There we go. Right, green bow tie. L1, so this angle up here, is equal to M2. Now, that doesn't really help us right now because M2 is outside both triangles. But because of those parallel lines, remember NM is parallel to KS. Because of those parallel lines, I have got alternate angles. So this angle M2 is actually an alternate angle to angle K2. I know there's a lot of scribbles going on. And so by the fact that both of them are equal, we can say that K2 is equal to angle L1. And so we've got another pair of angles in my triangles that are equal. So let's just take these scribbles off. I'm going to now do it without the bow tie situation, just so you can see. So angles in same seg, L1 is equal to M2, but M2 is an alternate angle to K2. And so that means that K2 and L1 are equal to each other, just by virtue of them both being equal to M2. L1 equals M2, angles in same seg. But M2 is equal to K2 because of alternate angles, because NM is parallel to KS, and so therefore K2 is equal to L1 because they are both equal to M2. So a very similar situation to what we had in the first question where we had to do a little bit of work before we get there. Now that I know that L1 is equal to K2, remember I automatically know that my third angle is equal. So I now automatically know that this whole angle over here in blue, NKL, is equal to angle S2 because of sum of angles in triangle. Once you've got 2, you automatically know the third is equal. So therefore, let's just move this down to put some space. Therefore, triangle LKN is similar to triangle KSM because of angle, angle, angle. We've proven similarity. Now, once again, girls, I'm fully aware that this is not necessarily the easiest thing to see straight off the bat. I do understand that. But that's why I keep saying to you, go back to what you've already proven. You've proven it for a reason. If you have proven K4 is equal to NML, it's for a reason. That was to help us find the cyclic quad. If you've proven it's a cyclic quad, it's for a reason. That was to now use angles in same seg. So all of the questions that we ask you, it's very rare that it's just a random question. They help you to go and find your next answer. All right, so I don't want your screenshots to get too teeny tiny here. So let's just take a screenshot of what we have thus far, and then we'll have a look at this last one here. There we go. All right, so take a screenshot of those two, and then we'll have a look at that last question, 11.2.3. Yeah. So if we have a look at 11.2.3, we've now been given some additional information. Again, I'm giving you information because it's useful. So we have been told here, so much going on, a bunch of different lengths. So we have been told that LK is 12 units, LK is up here, so that's 12 units. And we've been given essentially what is a ratio. So this 3KN is to 4SM. If you consider what this means as a ratio, if you go and essentially divide both sides by SM, you would have KN over SM, and then divide both sides by 3, you would have 4 over 3. You have a ratio of what KN to SM is. So KN over here is 4 parts. SM down at the bottom, 3 parts. Now, guys, what I want you to take notice of is the fact that all of that information, so the 12 units, the 4 parts, and the 3 parts, They all are sides in the triangles you've just proven similar. 12 units, so LK and KN are sides in the pink triangle. SM is a side in the blue triangle. Because they are sides in similar triangles, we can use the fact that corresponding sides are in proportion here. So this is now where we take the similarity statement and we set up those ratios. So remember, it's the first two, so LK over KS is equal to the second two, KN over SM, is equal to the first and last, LN over KM. And we know this is true because corresponding sides in proportion. You could also actually just state your similar triangle. So you could actually just state as a reason triangle LKN similar to triangle KSM. That's absolutely fine. It's telling you the same thing. So up to you. Right, so now that we have all of that, we can go decide what it is that we want to use. We're trying to find the length of KS, so I definitely need to use the ratio that has KS in it. Now go back to what you were given. You were given LK, KN, and SM. There's LK, there's KN, there's SM. So I'm going to use the first two fractions in this ratio here. So if I set that up for myself, so LK over KS is equal to KN over SM. Bearing in mind, I'm looking for KS. Now, KS is in the denominator, which is not an ideal situation, but remember, these ratios you can just flip. You don't have to keep it like that. So this can just flip to be KS over LK, but then just remember to flip the other fraction SM over KN. And now if we want KS alone, KS would be equal to SM times LK over KN. You don't have to do it like this, guys. I just like to isolate what I want, but you don't have to do it like this. And from here, you can now substitute what you have. So SM, remember, is the 3 units or the 3 parts. LK was the 12 units we were given, so 3 times 12, over KN, which was the 4 parts we were told. And then you just put that into your calculator. You don't need to do anything else. Telling you that KS is equal to 9 units in length. All right, so what was really important here is that taking the information that you were given, you matched it up to the sides that was appropriate, and you saw that those sides were part of or sides in your similar triangles that you had just proven. Because they were sides in the similar triangles you had just proven, it meant that you could set up your ratios and you could then go and use a ratio that was equal to each other to work out what KS was. So because all of those sides were sides in your similar triangles, you could use the ratio set up from your similar triangles to work out the missing length or the wanted length of KS. So this is why it's also so important when you are reading information of a question, and I mean, it works for some, it doesn't work for others, but this is why I put my information on a diagram so that I can visually see where it is, what it relates back to, how can I use this information I've just been given. Right. Any questions, grade 12s? If not, please do take a screenshot. And then remember, tonight is Wednesday, so it's a quiz night. Please make sure you are doing your quizzes. Not a lot of you are doing your quizzes. Please do, because your parents ask, and then you just have to say, well, they're not doing it. So please do your quizzes. It's on the Google Classroom, will be on in the next minute. It forms part of your continuous consolidation and revision. So doing those quizzes is really important leading up to your exams because it's just continuous revision for yourself. And then don't forget, on Monday, we're starting with analytical geometry, which is a really, really nice section. It's in paper 2. Paper 2 typically is the harder paper for some. And so analytical geometry is a place where we can get marks. Emmanuel, honestly, practice. And I know that's like, I feel like it's the excuse of every maths teacher, but it really is. I did not have a very good geometric eye when I was at school. I really struggled with Euclidean geometry. I didn't see things very well. And to be fair, there's still times now where I'll look at a question, I'm like, no, I've got no clue. But I'm a lot better at it because of how much practice I have. So my advice is practice, whether that means you go back to grade 11 papers and you start there and you leave out the similarity and proportion for now and you get to that and you just focus on your circle geometry. The only way you're going to see it is to do practice. So as you saw with my beautiful bow ties today, I could see the bow tie, right? I couldn't draw the bow tie, but I could see that bow tie, and that's just come from practice of, I know what my circle theorems are. I know what I'm looking out for. The more you practice your theorems, the more you implement your theorems, the more you're going to be able to actually see them on a diagram. So again, I know it sounds like the thing every maths teacher says, but specifically with geometry, it comes with practice because it's visual. I can't tell you, I mean, I've given you before we did the first 2 lessons, I gave you Dr. CPT. So diameter, radius, cyclic quad, parallel lines, tangents. Those are the first things you should always identify. So that's why in this question here, right at the start, I highlighted my tangent, I highlighted my parallel lines, because automatically that's drawing my eye to them and it's making me aware of where they are on my diagram and allowing me to start identifying angles around them. So if anything, that would be my first point of call. The second you get a circle geometry question, go to Dr. CPT and identify those 5 things. Whether it means you highlight them for yourself or you, I don't know, whatever you're going to do, those 5 things, if I'm giving it to you in the information, you're going to use them. So if I'm giving you a diameter, you're going to use angles and same seg. If I'm giving you parallel lines, you're going to use one of the parallel line reasons. Exactly like we saw here. We use tan chord and we use corresponding angles. So this is the only thing I can sort of say, use it. Everything else, you just have to practice and train your eye to it yourself. So yeah, unfortunately not a quick fix. Dr. CPT is a good place to start though when it comes to analyzing your question initially. Cool, guys.